Welcome to the second video creation assignment, which is related with the Think Pair Share, that is a TPS activity, which I had presented the DC regulated power supply, the block diagram of the DC regulated power supply. Now, inside the block diagram, as a first block that we have is a rectification section. Now, in this video creation assignment, I'm going to deal with the rectifier section, that is the different types of rectifiers and its working in a brief. So we are going to start with rectifiers. So what does a rectifier actually do? That's what we are going to see now. So we know that the supply that we are getting is the alternating current AC power supply. So now what the rectifier is actually doing is it is converting the AC into DC. So a rectifier is an electrical device that converts alternating current which periodically reverses direction to direct current which is in only one direction. This process is what is called as rectification. We know that the alternating current AC is having both positive and negative half cycles. This positive and negative half cycle, which we have a periodic reversing in the direction, is now changed to a single direction. So we have a rectification process happening here. And now we are going to see the different types of rectifiers that we have to do this. So first one that we have is a half wave rectifier. The second type of rectifier we have is the full wave rectifier. And we have one more, that is a third one, that is a bridge rectifier. And now we are going to see in detail what all these types of rectifiers are. So the first one, that is the half wave rectifier. Now in half wave rectification, so we know that the input is a sine wave, alternating current. Now in half wave rectification, what happens is either the positive or negative half of the AC is passed while the other half is blocked. That is, we will have only the positive half cycles or only the negative half cycles over here. That is, for the input that we are passing, the output what we get will be only the positive wave or only the negative half alone. Because only one half of the input waveform is reaching the output. And one of the disadvantages is it is very inefficient if used for power transfer, because we have only one side of the half cycles, either the positive or the negative. And now we are going to see the working of the half wave rectifier, and that is being showed in this animation. So we have the AC input over here that is coming. Okay, and this is the circuit diagram that we have. We have a AC source, this is the diode, and we have a load connected over here. And this part shows you the output that we get at the load section. So when we see there is a positive half cycle coming here. In this time, the diode which is connecting here is getting forward biased. So during the forward biasing of the diode, there is a current flow that is taking place. But when it is reverse bias, there is no current flow. Okay, so that is actually happening here. See here, there is a positive half cycle, and this time there is a current flow. But when there is a negative half cycle, there is no current flow. You can once more view this. The positive half cycle, there is a current flow taking place, but in the negative half cycle, there is no current flow because the diode now is in reverse bias condition. So during positive half cycle, the positive wave, that's the positive output, comes here, but the negative half cycle is not appearing here. Again, the next positive half cycle reaches here, but the negative half cycle is not reaching here. So directly saying we are having only the positive portion over here. So this comes the real output of a half wave rectification section. We have actually a step down transformer connected here, from where the step down process of the voltage is happening, and after that the stepped down voltage is that wave is being passed through the section, whereby we have a diode and a load connected across it. So when this is input waveform, the output that we have is only the positive half cycles. And now during the calculation of the output DC voltage, we can see that the output DC voltage of a half wave rectifier can be calculated with the following equations. The two ideal equations that we normally use here is, the first one is VRMS, that is root mean square. RMS is root mean square. VRMS is equal to peak voltage divided by 2. Or else we can also use DC voltage. VDC is equal to peak voltage, which is represented by V peak. So V peak divided by pi. So these are the two equations used for the calculation of output DC voltage of a half wave rectifier. Now we are moving on to the full wave rectifier section. A full wave rectifier converts the whole of the input waveform to one of constant polarity. It can be a constant complete polarity of positives or negative cycles. So here actually both the positive as well as the negative cycle we are getting in the output section, but the polarity is now in the output section is now just positive, either all positive or either all negative. Now a full wave rectification converts both polarities of the input waveform to direct current and is more efficient than half wave rectifier section, because there we are missing one half cycle, but here in full wave rectifier we have both the cycles that is being obtained at the output as the output wave. Now here comes the we are going to see the working of the full wave rectifier. So in the full wave rectifier, it can be either a rectifier which is designed with the help of a center tap transformer, or it can be a normal transformer. So there are many options for the configuring the circuit. We can either go for a center tapped or a bridge rectifier section. So in a circuit with a non-center tap transformer, either 4 diodes are required instead of the one needed for half wave rectification section. For single phase alternating current, if the transformer is center tapped, then 2 diodes back to back, that is anodes to anode or cathode to cathode, can form a full wave rectifier. Now this is the circuit diagram of a full wave rectifier using 4 diodes. We can see the input waveform, and we can see the output waveform, whereby we have all the positive cycles. So this is a non-center tap transformer used over here with 4 diodes. Now full wave rectifier section using a transformer, a center tap transformer and 2 diodes is being shown here. So we have a transformer, this is center tap transformer, and these are the 2 diodes that is being connected here, and we have a load that at the output section. So what is actually happening here is, when there is a positive half cycle coming here, one of the diode gets conducted, and the first diode D1 gets conducted, whereas D2 is reverse biased. So D1 conducts, and we are getting that positive cycle in the output, whereas during the negative half cycle, the D1 is getting reverse biased and your D2 is getting forward biased. So diode D2 helps in getting the waveform, that is a cycle, half cycle in the output section. So at a time, only one of the diode is conducting, and that half cycle is being passed to the output section. So during a time positive half cycle comes, and during the next time the negative half cycle comes at the output. So in together, as a total result, we are getting the complete waveform. Now we are coming to the formula. The average and the root mean square output voltages of an ideal single phase full wave rectifier can be calculated using the formula VDC is equal to V average voltage, that is V average is equal to 2 Vp divided by pi. Vrms is equal to Vp by root 2. So these are two formulas that is used for the calculation of average and the root mean square output voltages of a full wave rectifier. This shows the output voltage of the full wave rectifier, that is animation. Now coming to the bridge rectifier, which is used for the full wave rectification process. A bridge rectifier makes use of 4 diodes in a bridge arrangement to achieve a full wave rectification. So this is the circuit diagram where we have 4 diodes connected in a sort of bridge arrangement, whereas this is a transformer, step down transformer, and the two ends of the secondary of the transformer is connected to the diametrically opposite edges of this bridge circuit, and the load is connected across the other two diametrically opposite points of the bridge circuit. And now bridge rectifier, this shows you the bridge rectifier working animation. That is, during a positive half cycle, the diodes, this diode D1 and this diode D3, these two diodes is getting forward biased, and this helps you for the output that you're getting here. So one of the positive half cycle comes at the output. During the negative half cycle, these two diodes will be helping you. These two diodes will be forward biased, and those two diodes helps you to get the output waveform. That is the negative half cycle now comes to the output side. So this sort of a bridge circuit helps you to get both the positive as well as the negative half cycles, but with a single polarity. So the animation is clearly showing you which all diodes are getting forward bias during the positive half cycle and which all diodes are getting the negative reverse biased in that same cycle. Similarly, in the negative half cycle, which all diodes are positive forward biased or negative biased. The red color shows you the positive edge and black color shows you the negative end. And with this, we are winding off this section explaining the working of all the 3 types of rectifiers, that is the half wave rectifier, full wave rectifier, the 2 cases, that is using a non-center tapped transformer and a center tapped transformer, and also the bridge rectifier section is being dealt here. Thank you.